Does the way that we do concept development really matter? This is a case study. The same product, using the same team and the same starting data, but following two different methods for concept development. Out of it, there are three major categories of information that separate these methods. First is the output type, the problem found versus design inputs. Both methods found the same central risk. Traditional concept development exited with a restatement of it. Using Pierce the Design Fog methodologies, we exited with design inputs quantified by tying them to specific users, specific scenarios, and specific failure modes. The second category of information that separates these methods is the critical to quality. Three critical to quality attributes went in as part of a green light packet. Traditional concept development came out with three, the same three. Pierce the Design Fog came out with 7, with 4 new critical to quality targets, none of which existed in the green light packet, but all derived from failure modes. The third category of information were the action items and the teamwork involved. Traditional concept development aligned the team. The sessions ended with no names and no dates on the open items. With Pierce the Design Fog methodologies, we're more deliberate with teamwork, and we closed every session with a named owner, a deliverable, and a date, every session. Both methods found the right problem. Only one produced the design inputs, the critical to quality targets, and the accountability structure to do something about it. The rest of this video is the proof. Before we get into the details of what each method produced, let me explain why this product is a fair test. The Luminos Secure Pro is a fictional product. We're using a fictional company. We created a green light packet for this product, which is a lot of the market analysis, technical feasibility studies, and all the information that a company usually uses to green light a product for development. The Luminos Secure Pro is a product idea, a high-end smart home lock and AI video doorbell. It's a consumer product that is electromechanical. The AI component is not cosmetic. It processes video, recognizes authorized users, and makes the real-time decision to actuate the deadbolt. That decision layer is what creates the premium experience. It is also what creates a new category of failure modes that a purely mechanical product would never have, because now the software state and the mechanical state can disagree. Morgan is the buyer. She's security conscious. She evaluated this product on premium positioning, reliability specs, and brand. She made a deliberate decision to invest in home security, and she expects it to work. Her risk is not the device failing in a lab test. Her risk is the device failing in a way that makes her feel foolish for buying it. A false alarm locked out with guests waiting. A breach she didn't know about until after the fact. If it breaks, she calls customer service, writes a review, and tells her neighbors. Another user is Sam. He's entering and exiting the house early mornings and winters with groceries in both hands. His phone battery is at 12%, and he needs the device to work without a perfect setup, without the app open, without cellular signal, without a fully charged phone. The mechanical override is not a fallback for Sam, it's the actual use case when things go wrong. If Sam cannot get in, that is a return. If Sam gets locked out in dangerous conditions, that's a liability. The conflict is real. Morgan's requirements push toward AI sophistication and feature richness, which adds cost and complexity. Sam's requirements push toward mechanical simplicity and physical reliability, which competes for the same budget at $188. There is no version of this product that fully satisfies both without explicitly specifying where the trade-offs land. Any concept development method that does not separate these two users will drift toward designing for the buyer, because the buyer controls the purchase, but the end user controls the return. And the financial stakes make this case study concrete. The $188 cost target is not aspirational. It's a line between Grade 2 security positioning and commodity lock. Miss it, and the margin math breaks. Hit it by trading off reliability, and the returns eat the margin away. The program has 4 kill gates: cost compliance, critical to quality validation, supplier confirmation, and regulatory clearance. Missing one does not slow the program, it stops it. Phase Gate 1 is coming up fast. This is not an abstract product, even though it's fictional. This was designed to be a program with a credible path to failure, and is set up for our concept development test. The control for our case study and our experiment is clean. It's the same AI model on both runs, using the same team. Our team is made up of different agents representing different cross-functional areas of product design. We use the same team for both of our scenarios, one with traditional concept development and the other using Pierce the Design Fog methodologies. This team had the same starting document, which is our green light document, used to approve the product for concept development. There was no coaching between runs. Process architecture, and that's the process of how we do concept development, is the only variable. Let's talk more about this scenario and the two-user problem. Because one structural difference between the two concept development methods that we use is how each method handled this problem. Our two users have conflicting needs. Morgan wants seamless digital convenience. Sam needs a reliable mechanical fallback when the electronics fail. If you design for one and let the other erode, you get returns. Traditional concept development referenced both personas throughout. The team knew about Morgan and Sam, but there was no structure that kept their needs separated as distinct design streams. The buyer-user tension was discussed, but it wasn't really tracked. Using Pierce the Design Fog methods, the team separated Morgan and Sam from session 1. In the concept space model, the team created a distinct stream for each user's core benefit. Every session that followed maintained that separation, preventing design conflicts from re-emerging silently in later rounds. Each design put in the final output is traceable back to a specific user, a specific scenario, and a specific failure mode. When engineering gets a design input linked to a specific person in a specific situation, they don't have to guess who the spec is for. That is one of the differences that came out of doing concept development with these two methods. Now let's talk more about the outputs of concept development and differentiate between problem found versus actual design inputs that engineering can use. Both methods found the dead device scenario. This is where there's a total system failure. The main power and the battery backup are both depleted, and users are locked out in the cold. The team knew it was the central risk. It came up in round 1 for traditional concept development, and it kept resurfacing. Here's what 5 rounds of the traditional concept development process produced on that risk. The team aligned on needing a mechanical override, but must define vulnerable user capabilities and stress conditions before finalizing force torque requirements. That's a restatement of the problem, not a design input. 5 rounds in, and the team knows what needs to be answered. They have not answered it. Here's what Pierce the Design Fog produced on the same risk. The concept space is 3 user-centric focuses, each paired with a deep dive session. What the concept space model session surfaces, the paired session quantifies. Each one hands its output to the next as a working input. The concept space model benefits trace the automatic alignment benefit. the passive self-centering interface that lets the lock fit any door. The team asked, what is the physical limit of that interface? If door warp exceeds it, the override fails. That limit had never been specified. In looking at the concept space model symptoms, the team found 2 severity 6 risks: a dead device and a silent breach. The root cause is not the algorithm. The software state and the mechanical state can disagree, and that's a hardware problem. That distinction determines where engineering focuses for the next 6 weeks. And finally, the concept space model use process scoped the dead device recovery loop with a specific user in a specific moment. Who actually uses the mechanical override, under what conditions, with what physical capability? That question produced a design input, not validate force torque requirements for a vulnerable user. That is what traditional concept development produced after 5 rounds, a question. With Pierce the Design Fog methods, the team produced maximum actuation force at -20°C for a user with cold impaired grip and limited mechanical advantage. That is a testable design floor. Engineering does not have to reverse engineer intent. The context is in the input. The other 3 new critical to quality items follow the same pattern. A different focus in the concept space, different user scenario, but with the same specificity. Now let's take a closer look at what each method added to the critical to quality list. The green light packet had 3 critical to quality attributes going in. Let me show you what came out. Lock actuation reliability, AI false positive rate, app latency. Those 3 went in. Traditional concept development came out with the same 3, correctly identified that all 3 are in tension with the cost target. This is a useful finding, but the critical to quality list didn't change. 3 in and 3 out. With Pierce the Design Fog methods, the team came out with 7. The 4 new ones each came from a specific part of the concept space, and each one is traceable to a specific user, scenario, and failure mode. SAM must be able to tell a dead device from a frozen one without power from the use process. If SAM cannot distinguish the states without a visual cue, he runs futile digital retries until he gives up or forces his way in. The passive indicator is now a specified design input. The lock must seat and operate on any door across all temperatures. Benefits surfaced it when the team traced the automatic alignment benefit to its physical limit. If the door warps beyond the tolerance, the override fails, and Grade 2 security fails with it. The use process formalized it as critical to quality. The sensor alignment must hold through temperature swings. Symptom impact traced false alarm fatigue, not to the detection algorithm, to the sensor physically drifting out of alignment as the housing expands and contracts. Fix the algorithm, and you have not fixed the problem. Specify the clearance tolerance, and you have. This is a hardware spec, not a software fix. And finally, SAM must operate the mechanical override at -20°C with cold hands. It came from the use process dead device loop. The spec has to cover SAM in that moment, not the average user in a lab. The original 3 critical to qualities define what the product must do when it works. These 4 define what it must do when something goes wrong. Returns do not come from failing a lab spec. They come from SAM, locked out in January, hitting a scenario the team never specified against. That's the critical to quality delta. Now let's talk about teamwork. We don't want to underestimate teamwork. Traditional concept development produced real alignment. The team debated hard problems and reached consensus. And round 5 exits with things like this. The team agreed that a high silicone alloy is required for reliability, but must secure a supplier quote confirming cost and cycle time before proceeding to tooling. That's true. There's no owner, no date. The team agreed, and the session ended. Without being intentional about what the working session needs to produce, and without dedicating a formal part of the process to teamwork, that is what you get every time. The insights are real, the alignment is genuine, and then everyone goes back to their calendars and the work either happens or it doesn't. Pierce the Design Fog closes every session with a teamwork round. Not a summary, a handoff. Everyone ended with a name, a deliverable, and a date. Concept development doesn't fail because people are not collaborative. It fails because alignment doesn't automatically convert to action. People leave the room with shared understanding and individual calendars. The next priority wins. The teamwork round is the mechanism that prevents rounds from dying in the meeting room. Without it, the severity ratings and the failure mode decomposition are analysis artifacts. With it, they become engineering inputs with owners and deadlines attached. You do not get this by asking people to be more accountable. You get it by designing it into the process. This case study was not designed to show that traditional concept development is wrong. It's the standard. Teams make it work. A capable team running it will find real problems, and the Luminos team did. The question this case study answers is different. What does concept development output need to look like for a margins-focused, returns-risk product to survive to phase gate 1? 3 things. Failure modes classified by severity, so engineering knows what cannot be traded off against cost. Critical to quality items derived from how the product fails, not just how it should perform, so the spec covers the scenarios that actually drive returns. Accountability built into the process structure, so the work done in concept development becomes the work engineering starts from. Pierce the Design Fog produced all 3. Traditional concept development produced one of the 3, partially. Pierce the Design Fog gives engineering specific design floors to validate against. Traditional concept development gives engineering a set of questions to go answer. The difference determines whether phase gate 1 is a decision or a delay. A few closing thoughts. For this case study, both concept development runs used a Quen LLM. The traditional concept development team was as capable as the Pierce the Design Fog team. The difference in output comes from the process structure, not the people. If anything, that makes the case stronger. A highly capable team running traditional concept development still exits with open questions and unknown action items. The method is the constraint, not the people. This video does not teach Pierce the Design Fog methodology. It shows what Pierce the Design Fog produced versus what traditional concept development produced on a realistic product with a controlled setup. If you want the method, the concept space model, the tiered structure, how benefit impact and system impact work, how the teamwork round is designed, that's in Pierce the Design Fog. And on the results themselves, we've had case studies about solar panel service process, a portable oxygenator, a field lettuce harvester, and now Luminos Secure Pro. 4 different product categories, 4 different risk profiles. The structural output gap showed up in all of them. These consistent results across that range are not an argument about Pierce the Design Fog. They are what process architecture does to output quality, and that is the data point this series is building. I reference the other case studies in this series, and the links are in the description. And if you want the method, Pierce the Design Fog is in the description as well. Thanks for joining me on this case study. This has been a production of Dini Enterprises.